Okay, do you hear me? Yes. Okay, this is joint work with Claudia Faggian from IRIF and Daniele Pautasso from Università di Turin. So a little anecdote. Before yesterday, I lost my laptop and my slides were on it, and they weren't backed up. So I did my slides again from scratch this morning. So maybe they will not be very fancy, but still. Okay, so we start from a very simple graphical model. These are Bayesian networks. This is an example of a very, very simple Bayesian network. So we have a random variable, a Boolean random variable. This is rain, where rain can be true or false, and can be true and is true with probability 0.2, is false with probability 0.8. And then we have another Boolean random variable, wet grass. And so the probability of the grass being wet depends, of course, on the fact that it has rained or not. And so the probability of the grass being wet is defined by the table there. So this is a Bayesian network. So what is a Bayesian network? In general, it is a directed acyclic graph together with some conditional probability tables which are attached to each node. And Bayesian networks describe our knowledge of a portion of the world, let's say. And what we would like to do using Bayesian networks is Bayesian inference. And so everyone knows that Bayesian inference computes the posterior distribution, so the knowledge that we have once we have some evidence, once we have observed some facts about the world. And the posterior is proportional to the likelihood multiplied by the prior, and it is normalized by the probability of the evidence. So, for example, in this case, we could ask ourselves, what is the probability of rain being true given that the grass is wet? And we can compute it according to the previous formula, so using Bayes' theorem, as the probability of the grass being wet given that it has rained multiplied by the probability of rain being true, and we normalize by the probability of the grass being wet. So this is standard Bayesian statistics and standard Bayes' theorem. And so why do we use Bayesian networks? And why don't we just use standard Bayesian reasoning? So the pros of Bayesian networks is that they are very simple. So we are very constrained in the description of our model because it's a directed acyclic graph. And in particular, we can represent using these graph and these kind of tables in a very compact way, possibly very large probability distributions, because we don't have to express the full joint probability distribution, but we just highlight the dependencies between the random variables involved. And in particular, we have very efficient in practice algorithms to do Bayesian inference using Bayesian networks, exploiting the graph structure of the network. So, is there also a downside? Yes, of course. Since it is a very simple model, maybe it is too simple. It's a first-order model, and it's not hierarchical in nature. It lacks expressiveness, the typical expressiveness of programming languages, and it lacks modularity, compositionality. So everything has to be described using this graph that can grow a lot. So, for example, let us consider a case in which we have a model that depends on time. So, for example, a Markov chain or similar kind of models. So, we can describe such a model using this notation from taken from the typical statistics books and typical statistics papers. So, it's called a plate notation or a template. So we observe that we have a state which depends on the previous state, so like in a Markov chain, let's say, and we have an observational prime which depends on the state S prime. So this is a template. This means that it can be unrolled a certain number, a finite number of times, for example, in the picture 2 times, and this is the resulting unrolling of the template. So it is a real Bayesian network, so the one on the right-hand side is an actual Bayesian network. So this is the notation people in statistics use. It's quite clear, I would say, but still it's not a formal notion. It's not properly mathematically defined. And so we ask ourselves, which is the actual semantics of the template, of the compact notation. And for example, how many random variables are involved? Because this is important. I mean, statically at compile time, using only the template, we cannot know if the template is more complex than this example. Of course, how many random variables are involved, and this is of course important because the number of random variables is the typical complexity measure used to evaluate inference algorithms in Bayesian statistics. So can we formalize all this? And so this is our contribution. Somehow, part of our contribution is in formalizing this kind of notation using tools from the programming languages theory. So we introduce, first of all, a higher-order probabilistic programming language, which is able to describe complex Bayesian models, such as this template notation, but we can encode recursion inside our probabilistic programming language, so we can describe arbitrary complex models, let's say. What is the point is that the normal form of our languages are standard Bayesian networks, are first-order Bayesian networks. So we can encode in our programming language a complex model, but then if we do the rewriting until the normal form, then we obtain a standard Bayesian network. So how is that possible? This is possible because we exploit intersection types to guarantee that only meaningful programs can be written, so programs that are somehow Bayesian networks. And this is our main theorem, which says that a term T is typable if and only if it represents a Bayesian network. So, and by representing a Bayesian network, we intend that it can be rewritten to a first-order term which represents an actual Bayesian network. So, our type system induces also the notational semantics, and this is fine, of course, and this is somehow standard in intersection types because intersection types are used to to define the notational models. But moreover, we can read from the type derivation of our term the graph structure of the Bayesian networks that the program represents. So we can read out the structure of the graph structure, we can extract it from the type derivation, and we can also read the cost of computing the semantics and so the cost of inference. So this is our calculus. It's quite standard, I would say. You can see that we have this bank constructor, so it's a call by push value like calculus, and it has just one probabilistic constructs here, and this is a sampling from a discrete distribution. Then there are types, and these are intersection types. And so the fact that there are intersection types is clear from the fact that we have bags of types, multiset of types. So a term can be given more than one type. But the interesting thing with respect to the probabilistic aspect is that our ground types are not, for example, Booleans, but are names. N is a set of names, and these ground types represent random variables. So using intersection types, we can keep track of the different random variables that are generated during the computation. So how do we achieve our goal? Well, let's see this in some points, so our techniques. So first of all, non-idempotent intersection types. So these are tool that has been used in the last years to observe quantitative properties out of programs and to characterize quantitative properties. And so we use this kind of tool to keep track of random variables, copied random variables, generated random variables. But we can keep track of these random variables at compile time, let's say, statically, without executing the term. Then we use geometry interaction, which is a technique rooted in proof theory, to do some data flow analysis on our program and to ensure that our denotational semantics is actually compositional, because this is not trivial. And moreover, this data flow analysis allows us to extract the graph structure from the type derivation. Then, as I have already said, we use a call-by-push value like lambda-calculus, and this is mandatory somehow, because sometimes we want to share samples, while sometimes we want to copy the sampling primitive and actually duplicate it. So call-by-push value allows us to force and find computation, and so it allows exactly that. And finally, since we compile to Bayesian networks, our normal forms are Bayesian networks, so our normal forms are not values. And so the writing theory of our language is a bit more complicated than the usual, and we need some more sophisticated rewriting techniques to handle all the cases. So what about our denotational semantics? And this has some nice properties, I would say. First of all, it's cost aware, and it's cost aware in two ways. First, because we are able to compute the cost of inference out of the type derivation. And on the other hand, more interestingly, I think, the way in which our denotational semantics computes the probability function, the probability distribution defined by a program, is exactly as inference algorithms for Bayesian networks do. So, for example, variable elimination. So this is particularly nice because other kinds of denotational semantics instead are not so efficient in computing. And second, our denotations are factors, which are the standard way in which people in statistics represent probability distributions in inference algorithms for Bayesian networks. So we don't have an exotic semantic domain for our programs, but still we use something which is very well known from the statistics point of view, which are factors, which are a generalization of probability distributions. So to wrap up, our main contributions are a higher order programming language, which is sound and complete for Bayesian networks. This means that we can represent all Bayesian networks in our language, and moreover, all the well-typed programs are compiled to traditional Bayesian networks, but still they can contain recursion and every complex behavior, which we have a factor-based denotational semantics, which is sensitive to the cost of inference. We have an operational semantics that rewrites possibly recursive and higher order terms to first order terms. And we have a method to extract the underlying graph structure from the possibly recursive and higher order type terms. So this is all. Thank you.
Great. Do we have any questions?
So for Bayesian network, which is not on the shape of trees, my understanding is that basic inference, the time complexity of the basic inference algorithm depends on the tree width of the graph. So does that, you mentioned about this cost-aware denotational semantics.
Yes.
Does that mean your cost-aware denotational semantics somehow compute this tree width-like parameter implicitly throughout the denotational definition or something?
Yes. The point is that when you have a variable elimination, the cost of computing the inference depends on the order in which you eliminate variables, and this order is implicitly inside the structure of the lambda term. So you could rewrite somehow the lambda term using some commutative conversions to change this order of eliminating variables, and so you would have also another kind of cost. But given a term representation, then the order of variable elimination is fixed.
Can the next speaker come forward? And do we have any other questions?
Yeah, another question about the cost awareness. So there's another aspect of complexity of inference in Bayes nets, results of Dagum and Luby about like maybe NP hardness of exact results, but also showing that if certain probabilities are bounded away from 0 and 1, then you can get efficient approximation and so on. Is there any way that you considered to sort of consider those kinds of constraints in terms of your cost analysis?
No, we didn't consider it. I mean, we didn't consider so advanced results. I think our algorithm, let's say, is just plain, let's say, variable elimination. So,
Any other questions? Okay, let's thank Gabriele.